In the name of Allah Almighty, the Beneficent, the Merciful, welcome to PH 101 Lab, and our today's experiment is experiment number 5, the study of variable g via simple pendulum. So we will be studying the gravitational acceleration g via a simple pendulum, and by variable we mean that using the pendulum which is known as the variable g pendulum. So if the pendulum is inclined at some angle, so what will be the effect on the value of g, which we will be explaining shortly. So the apparatus required for this experiment is the variable g pendulum. As you can see, we will need a mass which can be attached to the other end of the pendulum. We will need a stopwatch and a graph paper. So the purpose of this experiment is to measure the time period t as a function of effective acceleration g in the subscript ef, g effective. So we will measure the time period of this pendulum, which is the variable g pendulum, and we will check that this time period is a function of the effective acceleration g, ef in the subscript. And we will measure the time period for various pendulum lengths L. So these are the two objectives of this experiment. So we will explain these one by one. Let's move towards our variable g pendulum. So normally we know that a pendulum is something, we know that a pendulum consists of a string attached to a fixed support, and at the other end we have a mass or a bob of mass m. And we know that it is the length of the pendulum from the center of mass of the bob to the fixed end. So if this is the fixed part, and this is the length of the string, and this is the mass of or this is the bob of mass m. So we know that we call this a simple pendulum. We know that. So this is actually a simple pendulum. This is actually a simple pendulum. So our simple pendulum is normally inclined at 0 degree. So the inclination is 0 simply. It means that the pendulum is horizontally aligned. So it is at 0 degree. So we call this pendulum to be the simple pendulum. Now what I mean to say is, we will need to discuss some prerequisites. So we know that the time period of the simple pendulum is 2 pi under root L by g. So we know that from our previous knowledge, the time period of the simple pendulum, or the time required for a single oscillation of a simple pendulum, can be calculated via this relation. So this is t is equal to 2 pi under root L by g. Now normally for the simple pendulum case, this g is actually, or we can say that this g is actually g cos of alpha or cos of theta. So actually this alpha is the inclination. This alpha is the inclination. So if our pendulum, as you can see in this case, which we will be discussing shortly, it is inclined, so it is not like this. You can see that the pendulum is inclined at certain angle. So in our case, in case of simple pendulum, the pendulum is inclined at 0 degree. So if I put alpha to be 0 degree, cos 0 degrees is 1, so I will get L by g. So this is actually the time period for the simple pendulum when it is not inclined. So we will be using this relation for the case of simple pendulum. But now this experiment is to study the variable g. So it means that some parameter is disturbing the value of g. So that parameter is known as the alpha. That parameter is known as the alpha. This alpha. Now what is this alpha? We will be discussing shortly. Let's discuss the prerequisites simply. So we know that this is the time period of the simple pendulum. This is the length of the pendulum for the simple pendulum, and this g cos alpha can be replaced by g if the pendulum is not inclined or it is horizontally placed, or the axis is at 0 degree simply. So we will be using this relation for the simple pendulum case. Now but for our case, the situation is different, and the pendulum which we are using is not the simple pendulum, but we call it the variable g pendulum. It means that if the pendulum is inclined at certain angle, so you can adjust the angle, which we will be demonstrating shortly in our second part. So you can adjust the angle of inclination. So initially, if the pendulum was here, so it's simply, we can say that it's now the simple pendulum. But if I disturb this angle like this, so the degree scale, from the degree scale, I can say, let's say this is 840 degrees, or I can move it, or I can change it to 60 degrees, 30 degrees, 40 degrees as required. So this is actually the angle of inclination. Now this experiment is to study if I am going to incline this simple pendulum at a certain angle, or the angle of inclination of this simple pendulum is not zero, then what will be the case? Then what will be the effect on the value of G? If the pendulum is inclined at certain angle, what will be the effect on the value of G? And then we have two objectives of this experiment, which we will be discussing shortly. So this is simply the time period of the simple pendulum. Now, the mathematics involved in this simple pendulum, we should know. Now there are two angles, keep in mind. At the back end of this pendulum, there will be an adjustable screw. You can incline this pendulum at any angle you want. So initially it was at 0 degrees. You will measure this, the time period or whatever is required. Now you will then move it to, let's say, to 20 degrees, and you will measure the time period. Let's say then 30 degrees, 40 degrees, 60 degrees. And from that relation, we will calculate the time period. We will calculate the time period. And if the angle of inclination is changing alpha, then it will definitely change the value of G. So we will call that value to be the G effective. Now let's discuss this simple pendulum. So if the pendulum is inclined like this, let's say this is the fixed axis. So it is fixed here now. Now, and this is the pendulum. Keep in mind that this pendulum, we will be demonstrating it shortly. But if this is the fixed axis and this is our pendulum, so this pendulum is moving, or its oscillation is like this. So the pendulum is allowed to oscillate in this direction, and this is the fixed axis, or we can say that it's oscillating perpendicular to the fixed axis like this. So this is the fixed axis and its oscillation is in this direction. It's oscillating perpendicular to the fixed axis, and it is inclined at certain angle alpha. Let's say this is inclined at 40 degrees. So if this is the horizontal axis and our pendulum is inclined at this axis, let's say alpha. So this length of the pendulum is, in our case, it's not a thread, it's made of rod or a steel rod. So keep in mind that if here we have the mass, here we have the mass attached to the other end of the pendulum, and it is inclined at certain angle, let's say at 40 degrees. Now the value of G will be in this direction. We know that there are two components. One is this component, and the other component is in this direction. So right in front of alpha, so if we are having this alpha, we will be using this alpha here. So right in front of alpha, we are having G parallel. We are having the G parallel component, and we can call this component to be the G sin theta or G sin alpha, because the angle here is G alpha. And this component, which is perpendicular to this component, is GEF. We are calling this GEF, the G effective component. And this will be equal to, if this is G sin of alpha, this component will be, we are using G cos of alpha. So this will be our G cos of alpha. This is the effective component. And this component is ineffective component because it is parallel to the fixed axis. Keep in mind, this G parallel, we are calling this parallel component because it is parallel to the fixed axis. So in this direction, we are having no motion. So this is actually the value, that is the value of G that is effective is this value, because the pendulum is oscillating in this direction. So the G effective value will be this one, not this one, because there are two components, this component and this component. So this component is parallel to this component, and the component which is G cos alpha is like in this direction. So we will be using this G effective component for this variable G calculation, variable G pendulum, keep in mind. So this G cos of alpha, so it means that the G effective component is depending, we are calling this G effective because here the pendulum is inclined at angle 40. So it's disturbing the value of G. So this is our, this axis is our G effective component. Now keep in mind, if this is our simple pendulum, now differentiating between the alpha and the phi. So if this is our simple pendulum, and here in this case the inclination is 0 degrees, this is for just understanding the difference between alpha and phi. So if I disturb this pendulum from this mean position O to some angular, by moving it to some other distance or displacement, let's say I am calling this displacement to be phi. So I have disturbed this mass from the mean position to some extreme position, let's say A. So alpha is actually the angular displacement of the pendulum from the mean position. So we are calling this alpha, and this we are calling this phi. Keep in mind, the angular displacement from the mean position. Phi is the angular displacement from the mean position. And this alpha is actually the angle of inclination. So in this case, the angle of inclination is 0. So you have to differentiate. You should know the difference between alpha and phi. So this is phi and this is alpha. Now if this is, let's say, our simple pendulum, and the angle of inclination, let's say for this case is 0 degree, and let's say this is at mean position O. The mass is attached at the other end, or this is a bob of mass m. And I displace this bob from this mean position to this position. So the pendulum will cover some angular displacement, and we call this angular displacement phi. So we know the difference between phi and alpha. So what happened when I displace this pendulum m? It will move back to its mean position, because there is a restoring force. The gravitational force is responsible to move back this pendulum to its mean position. So what will happen? There are certain components. If its weight is acting downward, this will be mg. One component will be this one. Resolve this force. We know that the vector resolution. We will resolve this into components. So one component will be this one, and the other component will be this one. So this is actually the component which will be perpendicular to this component. Keep in mind, this is actually the component. This is our phi. Right in front of phi, we are having mg. If this is mg, this will be mg sine of phi. And the component which makes an angle of 90 degrees, this will be mg cos of phi. So clearly we can see that this component is responsible to move the mass of bob of mass m back to its mean position O. Along this direction there is no motion. The motion is along this direction. So I can say that this is our restoring force, or this is the effective component of the weight, or the effective component that is responsible to move the pendulum back to its mean position. Simple. So along this direction, mg cos theta, or mg cos phi has no use here. So this is the ineffective component. The effective component is this one. This is responsible to move the pendulum back to its mean position. So I can say that this restoring force is equal to mg sine phi. And the restoring force, I will use a negative sign, and it indicates that the pendulum, it indicates the restoring force. Simply, it indicates the restoring force. Now, keep in mind, this was for the case when the pendulum was inclined at 0 degrees. Now, we are using a variable G pendulum. This is not the simple pendulum. We are using a variable G pendulum. So, if I am using a variable G pendulum, we know that the G value we were using will be G effective, which was G cos alpha. We discussed it, which was G cos alpha. We discussed that the GEF, one component was the G parallel, which was parallel to this fixed axis. So we are not using this one. So we will be using the G effective component, which was right in this direction, which was the G effective component was right in this direction. So if I am using this relation, this restoring force relation, F, let's say, so I will, for this case, for the variable G pendulum, I will replace this GE by GEF. Keep in mind. So this will be actually the restoring force for this variable G pendulum. So this is actually written in your manual. So you should know what is GEF sine phi. So now we know two things for this case. We know now, we have derived this, that we will be using the G effective component, G cos alpha, alpha is the angle of inclination, the value of g depends on this angle of inclination. It means that the value of g changes with this alpha, because if this is 9.8 and I put this, if it is 0 degrees, this will be 9.8. If this is 10 degrees, then cos 10 will give some value, and that value will be multiplied with 9.8, and the value of g effective will change. So this is actually the understanding of this value, or the understanding of this equation. And the second thing we studied is the restoring force in this case is minus mg effective. Keep in mind sine naught. Yes, the component responsible was sine phi, not alpha. Keep in mind sine phi is the displacement from the mean position. The angle, this angle, this will be, sorry, phi. And if the pendulum is inclined like this, so this angular will be alpha. So we know the difference. So these are the two components. Now if you see your manual, there will be a relation. So the correct relation is m l phi double dot plus mg effective sine phi is equal to 0. So this relation is written in your manual, and it actually represents the equation of motion, for variable g, for this pendulum, for variable g pendulum. Now there is no need to derive this equation, you just have to understand the basic parameters. So this m represents the mass, L is the length of the pendulum, phi is actually the displacement, the angular displacement from the mean position, and this phi is again is the angular displacement from the mean position. The g value we will be using for this experiment is the g effective. G parallel is not used in this experiment, we know that. So this is actually the equation of motion for this case. Now to derive this equation, which is not the part of this experiment, but I will be doing it very quickly. To derive this equation, we need to understand the Lagrangian mechanics. So this equation is actually derived using the Lagrangian. So Lagrangian is nothing, but it's actually equal to, it is represented by L, and it is the difference between the kinetic energy and the potential energy. So L is equal to T minus V. So this is actually the Lagrangian. We call this the Lagrangian. This L is equal to T minus V. Lagrangian is the difference between the kinetic and the potential energy for such a system. So this can be a simple pendulum, this can be a spring mass system, this can be some other system. So this relation is derived from the Lagrangian, and I will be doing it shortly and quickly. So to derive this relation, ml phi double dot plus mg effective sine phi is equal to 0. Do not worry about this Lagrangian. There is no need to derive this equation. But for the sake of understanding and for the theory and calculations part, let's derive this very quickly. So if this is the Lagrangian, it is equal to the difference between the kinetic and the potential energy. This is actually the Lagrangian equation. So from where we got this Lagrangian equation, I am not going into the details. d by dt of partial L over partial theta dot minus partial L over partial theta is equal to 0. So this is actually the Lagrangian equation, and this is actually the Lagrangian. So T is simply equal to, T is the kinetic energy. So the kinetic energy is half mv square. Now in the simple pendulum case, if this is the length of the pendulum and the pendulum moves in this direction, so we know that in circle, if I select the point A and I move from point A to point B, if you want to understand the radian, you can check my playlist and you will find the way what is radian. So you can check it out. So this is actually the angle subtended theta. So if this is the radius and this is the length of the arc is S. So there is a relation, we call it the theta, S is equal to R theta. S is equal to R theta. The radian equation. We know that S is equal to R times theta. So in our case, this is actually representing a circle. So I can say that if this is the length of the pendulum, this is theta. I am calling this to be phi in our case. And let's say this this distance is S. This distance is this arc length from this position A to this position B. The pendulum moves from this position to this position. So it's subtending an arc S, and the length is L. So the relation will be S is equal to L theta in this case. I am replacing this R by L. So this will be S is equal to L theta, and theta is equal to S by L. So you can shift it according to your need. Now velocity is nothing but half mv square can be written as ds by dt. We know that time rate of change of displacement is the velocity. So I can write it like this: t is equal to half mv square is equal to half m ds by dt. So s is equal to L theta. So I can write it d by dt of L theta whole square. Now theta is the angular displacement. Theta is the angular displacement. So it depends on time t, and L is the constant. The length of the pendulum is constant. So I can move this L, or I can move it out. So T is equal to half, T is equal to the the kinetic energy is equal to half m, L can be taken out, L and d theta by dt whole square. Now keep in mind, we know that the angular frequency, the angular velocity is d theta by dt. The rate of change of angular displacement, the rate of change of the angular displacement with respect to time is called the angular velocity. So in derivative or in calculus, what we can do, I can replace this d by dt simply by theta dot. So it means the first derivative of theta. So if I am having two dots, it means the second derivative of theta. Keep in mind. So if this is the first derivative d theta by dt, I will place a dot here. So d theta dot means simply d theta over t. So instead of writing d theta by dt, I can write theta dot simply. So from this relation, I can replace this by theta dot. So kinetic energy is half m L square and theta dot square. So this is actually our kinetic energy. I can call this equation to be my equation A simply. Now let's move towards the potential energy. Potential energy, which is represented by V is equal to mgh. Now we know that again from the simple pendulum, if this pendulum move from this position to this position, it will cover some height h. This will be our phi. This component will be, if this is mg, this will be our, let's say this is the length of the pendulum. The length of the pendulum is L. Or I can call this L to be capital L, because we are representing this by capital L. So I can call this to be my capital L. Now keep in mind that this h can be calculated from, if this is L, this is the mg or the L cos L sine of phi, and this is this component from here to here. This is the L cos of phi. So actually this h is equal to L minus L cos of phi. L minus L cos of phi. So we have already derived this equation. H is equal to L minus L cos of phi. So H is equal to L into 1 minus cos of phi. Simply L into 1 minus cos of phi. So this equation can be written as V is equal to the potential energy can be calculated as potential energy is equal to, or V is equal to mgh. H is L into 1 minus cos of phi. So this is actually the potential energy. This is my equation B. Now subtracting the kinetic energy from the potential, subtracting the potential energy from the kinetic energy, what I will get? So I will get L is equal to, the kinetic energy is half ml square theta dot square minus mg L, this is phi, sorry, this was our phi. I can call this theta to be phi. This is the angular displacement, and we know that the angular displacement I can use the variable phi instead of theta. This is phi. So what will happen? mg L 1 minus cos of phi, right? 1 minus cos of phi, and this is phi dot square. So this is actually theta dot. This represents theta dot is actually d phi over dt, and it represents the angular velocity. Keep in mind, if it is double dot, it is representing the angular acceleration then. So it is the first derivative of phi with respect to time. Phi dot means. Now this is very simple. L can be written as half ml square phi dot square minus mgl, and minus into minus is plus mgl cos of phi, simply. Now using this relation, I can now use this relation to find the equation of motion for this case. So what will happen? First calculate del L over del theta dot. So I will be, if this is phi, again I will change the variables to phi. If I am using the variable theta for the angular displacement, so I will be using theta. But for our case, we are using phi. We know that difference between phi and, so this is actually phi, the angular displacement. Now differentiating this equation with respect to phi dot. So this will give del L over del phi dot is equal to, now keep in mind that this relation and this relation contains no phi dot. You can clearly see that there is no phi dot in this relation and there is no phi dot in this relation. But in this relation, I can see that there is a phi dot square. So what will happen? Half ml square is taken out because these are constants, and I will take the del over del phi of phi dot square. Del over del phi of phi dot square, simply differentiating each, so this will give 0, this will give 0, and these are constant quantities, these will be taken out. So I will get phi L over phi dot is equal to half m L square. So derivative of phi dot square with respect to phi dot will be 2 phi dot. So this 2 will cancel out with this 2. So del L phi dot is equal to m L square phi dot. So this is, we have calculated this one. Now to calculate the del L over del phi naught. The first one was del L over del phi dot. Now the second one is del L over del phi. So how to calculate this one? Del L over del phi will give, so you know that this relation, we will differentiate this relation star, let's say, this relation. So del L over del phi, so this contain no phi, this will be 0, this contain no phi, this will be 0, but this contain phi and cos phi. So the derivative of cos phi is minus sin phi. So I can clearly say that del L over del phi is equal to mgl will be taken out because these are constants, and derivative of cos phi is minus sin phi, So this is actually equal to del over del phi is equal to minus mgl sin of phi. Very simple. Now we are having this value and this value. I will differentiate this phi dot with respect to t, as you can see in the Lagrangian equation. This is the requirement. So if I differentiate this with respect to d by dt of del L over del phi dot, so what will happen? ml square is constant. So if ml square is constant, it will be taken out, and del phi dot with respect to dt. So if here we are having one dot, so instead of writing del phi dot by del dt, I will be using double dots now. So clearly phi double dot means del phi dot over del t. phi single dot means del phi over del t. Keep in mind, this represents the angular acceleration, double dot, and this represents the angular velocity. This is actually the angular velocity. This is actually equal to angular velocity. This is actually equal to angular acceleration alpha. Keep in mind. So I am not using alpha for the angular acceleration. Let's say I will be using angular acceleration. Now the Lagrangian can be simply calculated as the Lagrangian is equal to ml double dot. So this is actually, this value is actually ml squared phi double dot, and this phi del L partial L over partial phi is equal to minus mgl sine of phi. So the final equation of motion, or the final equation, will be ml square phi double dot plus one minus is here and the other minus is here. So minus into minus will give plus mgl sine phi is equal to 0. Now keep in mind, this g we are using for this case, so this will be our g effective. Now one more thing is, this is actually d by dt, and this is partial L over partial theta dot. So I sometimes call these to be d by dt, so you have to differentiate between these two, d by dt, and this is the partial L over partial phi dot. Keep in mind. So this is our final relation. You can take the L common. So if you take the L common and divide it by both sides, so this will be L, and I will remove this L from here. So this is exactly the same equation in your manual. This is exactly the same equation in your manual, and it represents the motion of this pendulum. This is actually representing the motion for this variable g pendulum. Now this is all about the g alpha, g cos alpha, but now we are moving towards the objective of this experiment. This was all the theory and calculation of this experiment. Now the objectives are very simple. If you know the theory, the g effective component, what is g cos alpha? Now you know that what is g cos alpha. Now the experiment is very simple. The experiment is very simple. Now there are two parts of the experiment. The first part was to study or to measure the time period as a function of alpha. The first part was this one, and the other one was to measure the time period as a function of L. So it means that in the first case we will keep the L fixed. In the first case we will be just changing the alpha. Initially it is at 0 degrees, then it is at 20 degrees, then 30 degrees, then 40, then 50, then 60, and we will be studying the time period. What will be the time period? And in the second case we will keep the alpha fixed. So let's say I fixed it at 70 degrees, and then I will keep changing the length. So how to change the length? At the end of the pendulum we are having a mass of m, mass m. So if I move it above, so the length is reduced by this much. So if you are moving this mass, you are changing the length of the pendulum. So in the second case we will be changing the length, and we will study that how it affects the time period. Now keep in mind that the time period for this case is 2 pi under the root L by G cos alpha. We know that this is L by G cos alpha for the case of inclined pendulum simply, or you can say that the variable G pendulum. Now we know that the time period is directly proportional to the square root of L, and it is inversely proportional to the square root of G cos alpha. So it means that if you are changing the value of alpha, and the other relation is GEFF, G effective is G cos alpha. So it means that if you are using different angle of inclination, your G effective value will vary simply. And if this alpha is changing, it's affecting your time period, the time period of the simple pendulum. And simply if you are disturbing the length of the pendulum, it's varying not linearly, but it's varying with the square root L of the time period is varying with the square root of L. Keep in mind. So you should be conceptually aware of these things. This is the time period of the simple pendulum. The time period is directly proportional to the square root of the length of the pendulum, and it is inversely proportional to the effective component of the gravity or the gravitational acceleration. And if you are changing the alpha, you are disturbing the value of g. The value of g will change. Definitely this alpha changes. So if this is 9.80, let's say, and this is cos 10 degrees, so this will be some value, and that value will be g effective. So let's say if this is 9.8, cos alpha is, let's say, 10 degrees, so it will give 9.65. So it is actually equal to 9.65 meter per second square. So if your angle of inclination varies, your value of g also varies, 9.65. So this is actually the g effective value. The g effective value is g cos alpha. Keep in mind. Now let's move towards the tables. So in the first table, the analysis part, we will be using the variation of angle of inclination alpha, as we discussed. The t is a function of alpha for fixed length L. So the length can be of any value. It can be 15, it can be 16 meters, but it should be fixed. So I will recommend 15 centimeter to the length of this pendulum from here. Let's say this is 30 degrees. So the mass should, let's say I fixed it at 15 centimeter. So the mass is, let's say, here now. So I will first fix the mass at, let's say, the required distance is, let's say, the required distance is 15 centimeter. Now the length is fixed. Now I will change the value of alpha. Initially the pendulum is at 0 degrees. So the angle of inclination is 0 degree. Now g cos alpha is very simple. G cos alpha will be the value of g. Keep in mind the actual value of g. Actual value of g, or the experimentally determined or the accurate value determined, is 9.80 meters per second square. Keep in mind this is the actual value of g. Now what you have to do is 9.8 into cos of 0 degree. So cos 0 degree is 1. So this is actually 9.8. This will be 9.8. Now the t measured. Now this is actually the time period. There are two time periods. The first one is to using the stopwatch. So we know that if this is the simple pendulum, so one oscillation is if this is the extreme position A and this is another extreme position C. So if I move this pendulum from here, let's say the pendulum starts here. Let's say I move this pendulum here. Now if I release this pendulum at point A, it will move towards point B and it will come back towards point A. So the time taken by the pendulum to move from A to C and then back from and then C to A back is actually the time required for one oscillation, and we call this the time period. So one oscillation is when the pendulum moves from one extreme position to other extreme position and come back to the extreme position. Means the pendulum starts at point A, move to C, and it comes back to A. So you will note the time using the stopwatch. As you release the pendulum at point A, you will start your stopwatch. And as it moves towards C and come back towards A, you will stop the watch. So the time taken will be your time period. So let's say this is 0.816 seconds. The time required for one oscillation. When the pendulum moves again, when the pendulum moves from A to C and come back to original position A or the extreme position A. One oscillation from A to C and then again from C to A. This is one oscillation, and the time taken can be determined easily using the stopwatch, or you can measure it simply using the stopwatch. So this is actually the time measured using the stopwatch. Let's say this is 0.816 seconds. And the other way to measure the time period of this pendulum is using this relation. And keep in mind, this is for the case when the pendulum is inclined at certain angle. So for the first case, it is simply the simple pendulum. Because the alpha is 0, the inclination is 0. But for other cases, cos is alpha is changing. So what you have to do is t is equal to 2 pi s constant under root L by G. L, you can easily measure this length of this pendulum using a meter rod or a meter stick. So let's say the length, so for our case, keep in mind, so for the first case the length should be 15 centimeters. So you will fix initially, before proceeding, you will keep the length to be 15 centimeter fixed. You can keep it at any distance. You can keep it 16 centimeter, 20 centimeter, but you have to keep it fixed. So I will recommend to use 15 centimeter. So 15 centimeter is fixed. So L is 0.15 divided by G is 9.80, the actual value of G, and cos alpha is, for the first case, is 0. So this will give the value of T. Let's say this will give 0.76 seconds. Let's say this is 0.76 seconds. So there will be a very slight difference between the value determined, the value measured via the value measured using the stopwatch and using this relation. Now for the second case, the angle is now I will incline this pendulum at 10 degrees. Initially it was 0, then it will be now at 10 degrees. So the angle is now at 10 degrees. The angle of inclination is 10 degrees. Now again you will have to calculate G cos alpha. So G cos alpha is equal to, again, G cos alpha is equal to, G is 9.80, cos alpha is now 10 degrees. And we recently calculated this. This was equal to 9.65. This was equal to 9.65 meter per second square. So this will give 9.65. And again, you will have to measure the time for one oscillation from A to C and C to A. So you will use the stopwatch. You will start the stopwatch at point A, and as it moves from A to C and C to A, you will stop the stopwatch. So the time measured will be the time for one oscillation. You will record that time here. Now again, you will be using this relation to record the time period for the case when the angle of inclination is 10 degrees. Now you will repeat it for 20 degrees, for 30 degrees, for 40, 50, 60, 70, 80, up to 90 degrees. So at 90 degrees, cos alpha will be equal to 0. So if this is 0, the time period will be T is equal to 2 pi under root L by 0. So the time period will be undefined. So this is for the first case. The variation of angle of inclination when the fixed, for using the fixed length L is equal to 15 centimeter. So this was part first. Now in the second part, what we will have to do is to variation in length at fixed alpha 70 degrees. Now we will keep this angle of inclination fixed. So the fixed angle is 70 degrees. You will keep it at 70 degrees now. Now you will keep on changing the length of the pendulum, and you can do it simply by moving the mass above and below. You can change the length. So initially, if the length is 5 centimeter, so your mass will be here. Then it will be at 10, then it will be 15, 20, 25, 30. Let's say the length of the pendulum is 30. So you will be having 6 rows, 5, 10, 15, 20, 25, 30. So we are having 6. So this is for the first case, it will be 5 centimeter. Again, you will measure the time using the stopwatch. You will measure the time, and you will measure the time period using this relation. Then for 10 centimeter, you will measure the time period, and you will measure the time using this relation for 15 centimeter, for 20 centimeter, for 25 centimeter, and for 30 centimeter. So this was actually the purpose of this experiment. Now you know that as the alpha, the value of alpha is fixed 70 degrees, the G is 9.80. So I have already calculated this value to be G cos alpha is 3.6 meter per second square. In this case, your G cos alpha is fixed 3.36 meter per second square because alpha is fixed. In this case, L was fixed 0.15 meter, but this value was changing because alpha was changing. In this case, length is changing, but alpha is constant. So these are the two requirements or the two objectives of this experiment. And we clearly see that as the angle of inclination changes, you know that it decreases from 9.8 meter per second square to 9.65 meter per second square. So this is actually the purpose of this experiment, to study the variation in the value of G, or to find the G effective component when the pendulum is inclined at certain angle alpha. Now the other requirement for this experiment, that we have to draw a graph, the graph between the time period and the length of the pendulum. So we will have to draw a graph between the time period and the length. So you know that T is equal to 2 pi under the root L by G cos of alpha. Now if I take the square, this will be T square 4 pi square, this will be L G cos of alpha. Now dividing this L here, T square by L is equal to 4 pi square G cos of alpha. Now this T square is L is actually the slope. How? This T square is L is actually the slope. This is not mass, keep in mind this is the slope. M, slope is represented by normally by M. This is the time period square over the length of the pendulum. Now we know that the time period is directly proportional to the square root of L. So if I draw a graph between the time period and the length, it will not be a linear relation, because here the degree is 1 and here the degree is 1 by 2. So the graph will be, if I am increasing the length of the pendulum, the time period will increase. So it means that the graph will be like this. And on this axis we are having the length in meters, let's say, and on this axis we are having the time period T in seconds, let's say 1 second, 2 seconds, 3 seconds, 4 seconds. So if I draw a relation in this case, it will be like this. It will not be increasing linearly. So to calculate the slope of this curve, or to calculate the slope, what I have to do calculation, we will be plotting this graph as well, but for the slope calculation we will be plotting a graph between T square and L. This is the graph between T and L. This is now that the graph between T square and L will be a straight line. Keep in mind, this will be a straight line like this. So you will definitely, you will have some points on the graph, and when you will join these points, you will have some points on the graph, and when you will join these points, you will get a straight line. So how to find the slope? Simply, this is our time period axis and this is the length n in meters, and this is the time period in seconds. This is T square, keep in mind, this is for T square and L. So I am having some points. So this is point A, this is point B. So the slope can be easily calculated like this. This point is actually y2, the y value is y2 and the x value is, let's say this is x2. This is our x2. This point is actually x1 and this point is actually y1. So this is actually x1, y1 point. Now slope is equal to, we know that slope is equal to y2 minus y1 divided by x2 minus x1, or simply rise divide by run. This rise divide by this run. So this can simply be calculated by subtracting y2 minus y1. This value is y2, let's say this is 3 seconds and this is, let's say, equal to 2 seconds. y1 is 2 seconds. So 3 minus 2 will be 1. And let's say x2 is 0.5 meters and x1 is 0.1 meters, let's say. So x2 minus x1 will be, this point minus this point will be 0.4 meters. So this will give you the slope of this line. Simply, we will take 2 points, any 2 points. This will be, this point is x2 y2. This is x2 y2 point, x2 y2 point. And this is x1 y1 point. So y2 minus y1 divided by x2 minus x1. The difference between the y values and the x values will give you the slope. So you will put, so actually what I am doing, I am dividing T square by L. So that is why T square by L is the slope of this value. So this will be actually the slope. This will be actually the slope. So if this is the slope, you will have to find the value of G. So G will be equal to, G will be shifted there. This will be equal to 4 pi square into L divided by T square cos of alpha. Or simply, if you have calculated this value, this will be some value. Let's say this value is 11.5. Let's say, so your equation will be shift this G there and 11.5 here. So this will be G is equal to 4 pi square divided by 11.5 cos of alpha. So what will be the value of alpha here? Alpha. If this is 11.5 cos alpha. So keep in mind, this calculation is actually related with the second part, and in the second part we are using the value of alpha to be 70 degrees, so this will be actually equal to 70 degrees. So you will get a value of, let's say, 9.65 meter per second. This can be any value, but it will be close to 9.8 meter per second square. So this is actually your theoretical value. This is actually your theoretical value calculated using the graph. This is the value calculated using the graph. So at the end, we plotted a graph between T and L. So the graph will be like this. And then you will have to plot the graph between T square and L. So we'll get a straight line. We will find the slope between the y2 minus y1 rise. This is actually the rise. Rise is the difference between y2 minus y1. And the run. Run is x2 minus x1. So we will get the slope. This slope is actually, this is actually the T square axis divided by the length. So we will get the slope. So I will get a value for the slope. I will put the value here. Now I will find the value of G. G will be shifted here, and the value of that slope, let's say this is 11.5, it will be shifted here. Now 11.5 cos of 70 degrees, it will give some value. Divide 4 pi square divided by that value. You will get the theoretical value of the gravitational acceleration, 9.65. Now at the end, we will find the difference between the percentage difference. So it should always be less than, for this case it should be less than 5%, keep in mind. So the percentage difference, this is very important, is equal to the absolute actual value minus theoretical value divided by actual value multiplied with 100. And it should be less than 5% at least. So this was actually the experiment related with the variable G pendulum, that how the value of G is affected if you are inclining, or your pendulum is inclined at certain angle, and if you are changing that angle from 0 degree to, let's say, 90 degrees, your time period will change. Your G component will change. We are calling that component to be the G effective. Your G effective is changing. If your G effective component is changing, your time period will change. So this was actually the purpose of this experiment, that how the value of G changes if the angle of inclination of the simple pendulum changes. Thank you.